Okay, in this particular problem, we're going to look at the rate law problem again, but this one is going to be a little bit different, but it's relatively straightforward. So let me bring this picture up so you can see it. So what it says here is we're going to use the reactant reaction order to predict changes in the initial rate. A certain reaction is first order in N2 and second order in H2. Use this information to complete the table below and round your answer to 3 significant digits. So in the 3 columns that are given, we have 3 concentrations of N2, 3 concentrations of H2, and then 3 initial rates of reaction. Essentially, this is 3 different experiments. The first experiment is we put in a container 1.64 molar N2, 0.668 molar H2, and then we measure the reaction rate, how fast the reaction goes. That rate is 97.0 molar per second. In the second experiment, we put in different concentrations of N2, 7.33 molar, and different concentrations of H2, it's actually the same for H2, it's 0.668 molar. Then we're asked to determine the rate of the reaction. In the third experiment, both concentrations have been changed. The N2 is 0.205 molar and the H2 is 5.33 molar. The initial rate, again, is unknown, and that's what we're trying to determine. So I'm going to show you one method for figuring it out. There are different methods out there for this type of problem, but I'll show you one that's relatively straightforward, doesn't require too much advanced thinking, and we'll take a look at it. Okay, so the first thing I'm going to do is I'm going to write out the concentration of N2. Is 1.64 molar. Concentration of H2, 0.668 molar. And then your rate, initial rate. So this is the rate at the beginning of the reaction. It's a pretty fast reaction. The concentration is changing 97 molarity per second. Now, here's what I'm going to do. The rate law can be written as rate equals the rate constant times the concentration of N2 times the concentration of H2. Now, in the problem, they tell you that N2 is first order, so that's a 1. And they tell you that H2 is second order, so that's a 2. So we know those exponents. Now, what I'm going to do for that first experiment is I'm going to figure out what the rate constant is. I'm going to figure out what K is. So K, what I'm going to do is I'm going to divide the rate by N2 to the first. And then H2 squared. Okay. So I divided both sides by N2, so you have rate over N2. And then I'm going to divide both sides by H2 squared, so you would have rate over N2 H2 squared. And that leaves K all by itself. So in the first step, I'm going to write out what K is. I'll put the number over there once we get it. So the rate is 97.0 molarity per second. Concentration of N2 is 1.64 molar. Now that's to the first power. Concentration of H2 is 0.668 molar, but that's to the second power. So we have to make sure that we get that. Okay. Now, in order to do this problem, I'm just going to plug the numbers in. 97.0 divided by 1.64. And then I'm going to divide it by 0.668 squared. And you get 132.5. And I'm going to go ahead and leave an extra couple digits in there, 5.5. Now, we can also put the units in there. What would happen is these units would cancel. You'd have 1 over seconds. So that's reciprocal seconds. And then you'd have 1 over molarity squared. So that'd be molarity to the minus 2. So let me just write it out here a little bit more cleanly. 132.55 molarity to the minus 2 times seconds to the minus 1. Now, the key to this is that once you've got the value of the rate constant, you can do the other two parts. So in the second part, we're told that the concentration of N2 is 7.33 molar. The concentration of H2 is the same, 0.668 molar. And we want to know what the initial rate is. Okay, the question is, what's that? Well, we'll come back to this equation right here. The rate of reaction is K, so 132.55, m to the minus 2, s to the minus 1, so there's K, times the concentration of N2 to the first, so that's 7.33, times the concentration of H2 squared, which is 0.668 molar squared. Don't forget to square that. Okay. So that would be, let me go ahead and put this in here, times rate constant times 7.33 times 0.668. And I'm going to square that. Comes out to 433.54. But we don't want that many significant figures. We want just 3. So I'm just going to round this up to 434. Now, what are the units? This is divided by m squared. This is m squared right there. So those are gone. That's going to leave us with the m here and divided by seconds. So molarity per second. Okay, so 434. I'll put a decimal point there. Alex software typically wants a decimal point at the end. Okay, then we do the same thing for the third part. The third part is now 0.205 molar, 5.33 molar, and again, they just want us to figure out what the initial rate is. So we'll use this equation right here. The rate is equal to 132.55 m to the minus 2 seconds to the minus 1. Now we have 0.205. It's going to be a smaller number there, but this one's bigger. This has been jumped up quite a bit. And not only is it larger, we got to square it. So that's going to be probably a pretty big rate. It's probably going to be bigger than the second or the first one because you're multiplying it by 5.33 squared. Okay. So 132.55 times 0.205 times 5.33 squared. And you get 770. I'm going to round it immediately. 772. Again, molarity per second is typical units for rates. So 772. Okay. So the key to this one again is to figure out what the value of K is in the first step, because you know the initial rate, you know the concentrations, you know the exponents, you know the orders of the reactants. So essentially, you know everything but K. You figure out what K is for the first step. And then you can use that value of K in step 2 and step 3, and you can fill out that table.